So if you remember last time, when I introduced logarithms, I said, I mean, the reason that we came up with logarithms is because we can treat logarithms kind of like we treat exponents. The properties of exponents are pretty much the same as the properties of logarithms. So this thing here, properties of logarithms, you know, again, it's going to be kind of similar to the properties of exponents, or at least some of them that we've used before. I mean, I think when we did properties of exponents, we usually list about 7 of them, and we don't list 7 here. There's going to be a table which has 3 of them, plus one extra thing, which is the first thing. It's called change of base formulas. Okay. Right. So the change of base formula is it's a lot less necessary now than it was before. I mean, before, when we didn't have calculators that would calculate logs of any base, then we needed this in order to calculate logarithms. If you're using that yellow calculator in class, maybe you were issued by the school the black 83. Okay, the black 83 does not have log base in it. So you're going to have to do this kind of thing if you want to use the calculator to do logarithms of other bases. But basically, a change of base formula just lets you rewrite a logarithm in a different base. And you know, and what other base would we likely want to write it in? Well, I mean, what are the only 2 bases we have in our calculator? If we have an 83, log base 10, log base e, or ln. So, you know, in general, you can write a logarithm base a in terms of a logarithm base b, right? And in particular, if we use log base 10, the log base a, so any other base, becomes the log base 10 of x divided by the log base 10 of a. I mean, note here's log base a of x. So the x is here, and the a is here. You just do that divide, and you'll have something that's equal, right? And in terms of ln, right, again, the x goes here, and the a goes there. And you can use the ln button. It'll be exactly the same thing. And I think it was probably within the last year or so, I've said something to Miss Lang, who's the calculus teacher, about, you know, whether or not we still need to be teaching change of base formulas if everybody's got a log base function in their calculator. But in calculus, actually, you do need it. And I'll show you that in a slide or two. They don't want it to be the first time you've seen it when you get to calculus, and you need it in order to do derivatives and integrals that involve logarithms. Okay, so let's say this log base 2 of 12. We're going to do it twice. Once with log base 10s, which are called common logarithms, and one with log base e, which are called natural logarithms. Right, so log base 2 of 12. Using log base 10, it'll be log of 12 divided by log of 2. Right, and that you can put in the calculator, just like it is. Clear. Log of 12, make sure that you close it off, right? Otherwise, it's going to be putting everything inside the logarithm on top, and you don't want that. So close off log base 12, log of 12 divided by log of 2. That was wrong, clear. Log of 12 divided by log of 2. 3.585. Okay, try the same thing with ln. It should be exactly the same thing, right? It shouldn't matter which base you use. You should get exactly the same thing. Log base 2 of 12 equals ln of 12 divided by ln of 2. and it's the same thing, right? To the decimal point, it's exactly the same thing. So if you have to change from one logarithm base to another, that's how you do it. So even with an 83, you can calculate any base. If the question is just calculate the logarithm of a value, then you could just do that. Now, in calculus, the thing about in calculus is we need to be dealing with ln in calculus, right? ln, the natural logarithm, comes up in calculus naturally, right? I mean, it's kind of interesting that we will learn in the very last section of or chapter of this book, we learned about derivatives. Derivatives in calculus are functions that represent the slope of another function, right? And for most polynomials, the derivative of a quadratic is linear. The derivative of a cubic is quadratic. The derivative of a quartic is cubic, right? It's always one less degree. And we have very simple methods to find the derivatives for that. The interesting one is that if your function, right, if the function happened to have been ln of x, then the derivative, f prime of x, is 1 over x. If you take 1 over x as a function, that would describe the slope of the graph of ln of x for every value of x. Why is that? Why would ln and 1 over x be related like that? I don't know, but they are. Just like if another interesting one, right? If your function was e to the x, the exponential with a base of e, the derivative would be e to the x. It's the only function which its derivative is itself, right? This describes the slope for every value of x in the function e to the x, right? That doesn't happen for anything else. And those are some of the examples, along with what we saw, when we did the limiting value for the compound interest formula, we saw the e just kind of pops up there. It kind of comes up. So if we happen to have gotten a log function, some other base in calculus, we don't have these kind of nice relationships that just happen like that. But the thing is, we can always use the change of base formula, convert it to ln of x over ln of 10, because that's a base 10, right? And now you've changed the thing to the kind of function that you can deal with in calculus, and you will do that. Okay, you'll use change of base formula to change other logarithms to ln, because in the end, that's just a constant. Dividing by a constant is not really part of the process of finding derivatives or integrals. You just take the constant out and put it back at the end. So we need change of base formulas at the very least for that. Okay, now these are the properties. There's only 3 of them: product, quotient, power. And you can do them with log base A, meaning any base. So certainly you could do them with ln's, because ln is just the base is e. Okay, well, we already said you could do it with any base, so you can do it with ln. So notice the product property. If you're taking the logarithm of a product, right, inside the argument of the logarithm is u times v. You can break that up into 2 different logarithms: log of u plus log of v, right? So the logarithm of a product equals the sum of the logarithms. So again, that relates back to the properties of exponents, right? When we multiply exponentials with the same base, we add the exponents. That's all we're doing here. That's why this works. Okay. The quotient property. You're taking the quotient of or the logarithm of a quotient. That's the logarithm of the numerator minus the logarithm of the denominator. And the last one, the logarithm. If you have something, you're taking a logarithm of a quantity which is raised to a power, right? So this is u to the n. Then you can take that power in front of the logarithm as a multiplier, right? So that n there is now there. Now it's n log a of u. So if as long as that n is the exponent for the whole argument of what's inside, then you can take it to the front like that. Now what you don't want to do, which is a mistake, remember this is allowing us to take logarithms of products and split them up, right? We don't have another property like log base a of u plus v that allows us to split that up. Okay, you cannot, we don't have a property that takes the sum inside of the logarithm and breaks it into two things, right? It only works from the product to the sum of logarithms. So don't try to split that up. Same thing if it was the log of u minus c. You can't split that up. That happens. Now, most of everything else we're going to do now in this lesson is involved with using these properties either to take a logarithm, one logarithm, and break it up into many logarithms. That's called expanding it. Or it's taking many logarithms, like what's on the right-hand side, and then using these properties to write it as one logarithm. And that's called condensing. So the logarithm takes you from this side to this side. Condensing takes you from this side to this side. Expand, condense. And again, we'll be doing that with ln, we'll be doing it with other logs, doesn't matter. Now, when you look in the homework, I mean, their directions, although they use the word expand and they use the word condense, sometimes people get confused over what they're being asked to do. Right? Just keep in mind, because your homework problems come from these sections, and these are the directions. Right? Indeed, use the properties of logarithms to expand the expression as a sum, difference, and or constant multiple of logarithms. In the end, it's just going to be do what we're going to just show in a second about expanding. That's all you're being asked to do. Or in condensing, right? Condense the expression to the logarithm of a single quantity. But in the end, condense, expand, expand. Don't be confused with directions. So, for example, let's expand a logarithm. So how many things do we see going on inside of that? Do you see a product? Do you see a product inside that logarithm? Do you see a quotient inside that logarithm? Yeah. At the very least that. Right? So I can write this first thing, I can write it like this. That is the log of 4, log base 3 of 4, plus the log base 3 of x squared minus the log base 3 of the square root of y. You know, you're going to end up with multiple factors in the numerator and in the denominator. Okay? Just remember, when it's expanded, everything that came from the denominator has a minus in front of it. Everything that came from the numerator has a plus in front of it. Right? The 4x squared, they both have pluses. Yeah.
So it doesn't matter if you do the product first or the quotient.
No. I mean, I just did all one step like that. We'll do a couple more similar things. Okay. Now, we're not done yet, right? We're not done yet. Nothing we can do on this one. But this log base 3 of x squared, which property could I use to simplify that? The power property, right? That x squared, that x is being raised to a power, right? The entire argument of the logarithm being raised to the second power, so I can write that like log base 3 of 4 plus 2 times the logarithm of x. Right? Bring down the 2 in front as a coefficient of the logarithm. Now, even the last one can be simplified because you can represent a square root as being raised to a power. What power? To the 1/2 power. So if you need to, take a step and go log base 3 of y to the 1/2, and then you can use the power property again. 1/2 will go here. So this is log base 3 of 4 plus 2 log 3 of x minus 1/2 log 3 of y. And then that's complete, right? We've done everything. We used a little product property, a little quotient property, and power property we used twice. Okay, let's do a condense. Okay, so what do we see going on here? What is this subtract? Which property are we going to end up using for that? You're going to use a quotient property, right? And we can see that this entire thing is being multiplied by 2. There's probably going to be some kind of product property that goes on here. And there's actually that 2 in front of that logarithm. That's going to be a power property too. So let's see what we can do as a first step. How about I'm going to write, well, what property would I have to use first? Well, here's the thing. If I tried to put these two together with a quotient property, the quotient property does not include the possibility that there could be constants multiplying. I need to get rid of that constant multiplying. So what could I do with that too? Bring it inside, right? Bring it inside. So we really do have the difference of logarithms. Right now we don't have the difference of logarithms. So let's do this. It'll be 2 times the log of x plus 3 minus the log of x minus 2 squared. Okay, now we can use the quotient property because it is the difference of logs. Right? So that'll be 2 times the log of x plus 3, I'm going to keep that in parentheses, and x minus 2 squared. Right? Okay, now, is there anything else to do? Take that 2 as a coefficient and move it inside as a power, right? So that'll become the log, this is base 10, I guess, of x plus 3 over x minus 2 squared, all of that raised to the second power. Now we've got one logarithm. We condensed it. Now, I'm not sure the way, the book may leave it like that, or they might go like this. Log of x plus 3 squared over x minus 2 to the 4th. You could square the numerator and square the denominator. Yeah? I'd probably count that. I mean, I'm not sure one is all that much simpler than the rest. I mean, at that point, you have written it as one logarithm. I mean, everything else now is simplifying within the logarithm, which is not exactly the point of the problem. Now, I'm going to show one more example, which comes from an even number of the homeworks, because I didn't think that the 2 examples that are here were quite enough. But understand that above, I did like the check for understandings underneath, but there were more examples of both, right? Of expanding and condensing, worked out, absolutely all the way worked out. If you want to see more examples worked out, but I felt like we needed to look at this one in particular because it's the kind of problem that causes us trouble. I mean, how many logarithms are we trying to condense here? We got 3 logarithms, right? Which means when we put these inside of a fraction, which is inside of a logarithm, we got 3 factors, right? So remember what I said about if it's a positive logarithm, that means that argument's going to go in the numerator. If it's a negative logarithm, that means that one's going to go in the denominator. So once we combine, that's how you decide what goes up and what goes down. Now, am I ready to combine these into one logarithm? What should I do first? This 3 right here, we need to get that inside the logarithm before we condense, right? So this will be 2 times ln of x to the third minus ln of x plus 1 minus ln of x minus 1. Okay, now I've got single logarithms, so now I can put them all into one, which will be 2 times ln, okay, and which goes in the numerator and which goes in the denominator. The x to the third is in the numerator. Right, and then this is x plus 1, x minus 1. Okay, are we done? We still have to do what? We got to take this 2 and move it inside. So this becomes ln of parentheses x to the third over x plus 1 times x minus 1. That's not a very good one. Squared. That would be done. Let me see if I can do something here. It's not going to work. I don't think it's going to work. No. Maybe I can do this. No. I'm going to go down the board here a little bit. But a lot of times, this thing could be written like this, right? If let's say that I factor a minus out of both of these terms. Then it would have looked like this. 2 times ln of x to the third minus parentheses ln of x plus 1 plus ln of x minus 1. And when you've got that kind of thing going on, it gets confusing because that looks like a plus. Students want to think that means that it goes in the numerator, but you've got to get everything simplified. You know, distribute that minus, so you just have a bunch of logarithms, and each one has got its own sign, right? Don't try to take something like this and see that like it's a product, and that therefore it goes in the numerator. It is a product, right? It's a product of these two things in the denominator because of the minus in front. So what's best is if you get that situation, just distribute the negatives so that you know which term is positive and which is negative, and then put everything that's positive in the numerator and everything that's negative in the denominator. Okay. So I'm going to show you one more thing, which is not really so related. Is anybody taking stats? You taking stats now? Okay. I mean, if you see yourself taking stats someday, logarithms are used a fair amount in stats. Although we don't do much with it in the stats class. We do talk about it. I mean, I know that it's part of the AP exam, let's say. So let's look at this right here. I've already loaded the data in my calculator, so it's not going to take too long. So we're going to try to find a mathematical model. Right, this table shows the mean distance from the sun and the period, the time that it takes for the planet to orbit the sun for these 6 planets, which are closest to the sun. So in the table, the mean distance is given in terms of astronomical units, where the Earth's mean distance is defined as 1, and the period is also. So you can see Earth is 1 and 1 for the distance from the sun and for how long it takes to go around the sun. Right, so all these things, you know. Now, how could we, if we wanted to graph these and see if there's some relationship, then you make a scatter plot, right? So you go to your calculator and you go stat, edit, and you put the data under L1 and L2, right? And you look at the data. And some of this stuff, maybe you remember, maybe you don't. Second, y equals is the stat plot I turn on the plotting of points, right? It's set to a scatter plot. It's set to the scatter plot there, and then I look at it. And if I want to look at data in the calculator, then I go stat or zoom 9 for zoom stat, and you look at the points that you've got. Here's the first few points there, and then there's there, and then there's there. Now, what we would really like most of the time when you're in statistics, you want to see whether you can find correlations between the data. And by correlations, we mean linear relationships between the data. Does that look linear at this point? No, it doesn't look linear. So in statistics, if you get a relationship, it doesn't look linear, but it does look like there might be something there. Then you try to, like, you know, re-express the data. Maybe you take the data that you were given, right, this stat, edit, and you square everything. Square all these and square all these, replot it. Does it look straight now? No. Try to take the square root of all these and the square root of all these, plot it. Does it look like it's a straight line now? No. Okay, but one of the things they do is take the logs of them and see what it looks like and graph it. In this case, sometimes in the way that you would do that is maybe you would take the log of one of them only and then see whether now with the log of one compared with the other, is it straight now? If not, try the other one. If not, try them both and see what it looks like. This is one where it works out if you do them both. And if you've never seen this before, this is a way you can deal with the data in the calculator. You go like this. I want to put in, I'm going to take the ln of all of these values right here and put them here. Now, I don't have to do that 5, 6 times. All I'm going to do is this. I'm going to go over to the L3, right? And I'm going to say ln, right? I'm up there in the top of the column. It's saying ln, and I want to take the ln of L1. Well, L1 is on top of the 1. So I go second, 1. So it's going to take this column will be the natural log of everything in this column. Right. And then I'll do the same thing for the L4. I'm going to say ln, and this time I want it to be taking the ln of all these values. So I'll go second, L2, and that. And then I go back to my scatter plot. I can go second, stat plot, 1. This time I got to change, so it's taking it out of L3 and L4, because that's where I just put that stuff. Second, L3, second, L4, and then I do another zoom 9, because it's got to zoom in on those points. And you look at it now. Does it look like it's linear? Yeah, it does. You know, but so you use natural logs sometimes to re-express data, so you can get a more linear relationship out of it, and you can start talking about things like correlation coefficients and things like this. The truth is that if you looked at that original data, it had a pretty high correlation coefficient already, but when you straighten it out like this, then it ends up being correlation coefficient like 0.999, something like that. So it's very, very strong correlation at that point. So yeah, you can use the natural log to re-express data. If you get to that point in the stats class, you know, it may be just one of many things you try to do to re-express data to try to get a linear relationship. That's it. So we rewrote logarithms with different bases. We expanded, we condensed, and we looked at a real-world problem. And that is the end.